All right, let's review some topics in dynamics. Okay, let's go over Newton's laws. Newton's first law is commonly called the law of inertia. The law of inertia says that if I have two forces that are in equilibrium, then I have no acceleration. That means that it's traveling at a constant velocity or it's at rest. Notice, it doesn't have to be at rest. Just because the vectors canceled each other out doesn't mean that it's not moving. In fact, free body diagrams can only tell you about acceleration. Now, the airplane on the right has an imbalance of force. When you have an imbalance of force, you have to subtract the vectors going in one direction from the other ones in the other direction. In this case, the weight vector is the one that is winning. And so I find that difference between him and the lift. And whatever that difference is the mass times acceleration of the object. Let's go over some free body diagram rules. Make sure you only draw forces that are there, okay? Know when to stop to draw a free body diagram. You're just drawing forces that you know exist for that scenario. Don't draw vector components on a free body diagram question. You just draw one vector per force in the direction that it is applied. Also, the vector should be to scale. As you can see, on both helicopters, I drew the same size red arrow. That's because they have the same weight. But I had to show how the force of lift was losing on the right diagram, so I had to draw a smaller vector for it. Nothing can apply a force to itself. It's impossible. Once again, equilibrium doesn't necessarily mean rest. It could be a constant velocity going in a straight line. And most important of all, a free body diagram never determines the direction of a movement. It only tells you the acceleration and the direction of the acceleration. Let's go over the contact forces. The first force is the normal force. Now that does not mean up. A lot of students think that, hey, that's whatever force is going up. No, that's not true. A normal force is a force that is perpendicular to the surface of contact. So if the surface is going vertically, the normal force will be horizontal. And if the surface is at an angle, the normal force has to be 90 degrees against that angle. And friends, please only draw a normal force if you know there is contact between the object and surface. If there is no contact, then there is no normal force. Frictional force is kind of a complementary to normal force thing. Because whereas normal force is the perpendicular force, frictional force is the parallel force. If an object is moving, the friction is going to try to slow down the object and go in the opposite direction of motion. Now, if the object is at rest, the frictional force is only there to preserve rest. So let's say we have this object on an incline. That object wants to slide down the incline. So friction will oppose that falling by going in the opposite direction to preserve the rest. And finally, if something is rolling, the direction of friction is in whatever direction helps the roll. Now, we need to get straight static versus kinetic friction. Okay, here's the commonly seen graph that tells you the difference. So static friction is the friction that responds to maintain the system in equilibrium. So let's say I have a box on a surface there and I apply a force. Static friction will meet whatever force I apply to it to prevent that object from moving. So that's why on this part of the graph you have a slope of 1, meaning the frictional force is whatever is needed to be to keep the object at rest. However, static friction has a limitation. There is a certain point to where the static friction can no longer keep the object at rest. That's called the maximum static force. And with the equation for that one point on the graph is the static friction equals the coefficient of friction statically times the normal force. Once the object slips, then we are in the kinetic friction zone. And that's when you see a drop in the frictional force. So in that case, the frictional force is smaller than it was before, and the object is now moving. For kinetic friction, it's the same equation as the other one, except the subscripts have changed. Let's go over what the equation means. Okay, I call it the fun equation because that's just a good way and a fun way to remember it. Okay, basically the equation makes sense. It says the frictional force is directly proportional to the normal force, meaning if objects have more contact, if one object is pushing into the other more, then there will be more friction. There will be more rubbing. Now these coefficients of frictions are both smaller than 1, and the kinetic coefficient of friction is always smaller than the static coefficient of friction. I want to go over Atwood machines. Atwood machines are whenever you have two weights connected to each other by a rope and gravity is acting on it in some form or another. This is a kind of difficult problem because they put one of those blocks on an inclined plane. So the first question is normally draw a free body diagram. So to draw a free body diagram, you draw all the real forces that are acting on the object. Since both objects are on Earth, or we assume that at least, then they have weight going down pointing toward the center of Earth. Notice that I drew both vectors the same length. That's because they both have the same mass. Now, the next thing I'm going to draw is the contact forces. And in this case, there's no friction, so I'm going to skip that. But the box on the left has a normal force. And the reason why it has a normal force is because it is in contact with the surface. The block on the right does not have a normal force because that block is not contacting anything. What the block on the right does have is the rope trying to keep the block up. And the same thing on the left one, we have the rope trying to keep the block up the incline. You draw the tensional forces along the rope, and as you can see, that tensional force is parallel. Okay, what other forces are acting on this object? There are none, and that's where we stop. We're not going to add any irrelevant, non-existent forces. These are the only forces acting on the object. The next question asked is, what is the acceleration of block 2? So to do this, I need to look at my free body diagrams and see where there's imbalance. Now the free body diagram on the right shows me that the weight is going to win. So I'm going to call down positive. And the free body diagram on the left, it's on an incline. So I'm not going to use traditional x and y axis on this one. I'm going to use the parallel axis and the perpendicular axis. You're doing axes that are tilted because the direction of motion, you want to try to align that with one of the axes. And because our axes are at tilted and weight is kind of on both the perpendicular and the parallel, I have to do what I call a pseudo free body diagram. So the tension is fine because it is going in the parallel direction, and the normal force is fine because it is perpendicular to the surface. It's the weight force that is different than the other ones. It's because it's at an angle with one of my axes. And whenever you have a vector at an angle, you have to use trigonometry to find its components. Doing trigonometry would show you that the cosine of the angle would be on the perpendicular and the sine of the angle is on the parallel. The way to remember that is sine slides. That's a good statement to say, meaning that you use the sine of theta on the part of the diagram that would be sliding. Now that I have drawn my pseudo free body diagram and my other free body diagram, I can now start to approach the question. For the diagram on the right, I'm going to use Newton's second law. And the reason is because it's an unbalanced force. I need to see the difference in forces and set that equal to ma. Over there on the left on the pseudo free body diagram, For the axis that is perpendicular to the incline, I'm going to utilize Newton's first law, the law of equilibrium. I can assume that the normal force equals the weight times cosine because there is no acceleration happening perpendicularly. The object is not flying off the incline or being dug into it, so there is no acceleration in that direction. So I just use equilibrium. Now, parallel to the incline, I can't use equilibrium because the tensional force is winning. So I do Newton's second law for that as well. Now, with Atwood machines, you can make two assumptions. They have the same tension in both ropes. Being that it's one rope, it has one tension. And both objects have to accelerate at the same rate. That's because the length of the rope will never change. So with those assumptions, I need to now solve for acceleration. The best way to solve things when you have multiple unknowns is to get rid of the thing you don't care about by using substitution. I don't know t. It was not given to me. So on the left side, I'm going to solve for t and then plug that into that equation, combining both equations together. I plug in the tension and notice how the tension disappeared. Now I have one equation with one unknown, and I've bolded in the unknown. I apply that negative sign across, and I notice that what I'm looking for is on both sides of the equation. I'm going to add ma to both sides so that I can have my unknown on one side of the equation. And then finally, I can divide by m, which cancels out on everybody, and then divide by 2. And there's my answer. However, they did say that it was a 30-degree angle, and the sine of 30 is a half. I do that calculation, and I find out that the acceleration is a fourth of gravity. I want to show you an alternative method, and that's the method of defining a system. In this case, I'm going to define my system as block 1, block 2, and the rope that connects them together. And I'm going to consider them as if it was just one object. And that's useful because they do both have the same magnitude acceleration. And so I'm going to draw a little circle that represents that system. And that system has double mass because it has 2 blocks in it. Now, I'm going to draw all the external forces acting on the object. So the weight of block 2 is trying to make the system accelerate in that theoretical abstract direction. And the weight of block 1 is kind of holding back the system, making it go in the other direction. And I don't draw any other forces because those are either internal forces that cancel out or forces that were in equilibrium anyways. And now I can approach this as a simple sigma F equals ma. I plug in the double mass. I do a difference between the forces. The mass cancels out. The sine of 30 is 1/2. And then I divide by 2 to get 1/4 of gravity. The whole question now is changed. What if we were to replace that massless pulley from the previous question with one that actually has mass? And because it has mass and is now rotating, we have rotational inertia. It said that we could use a disk rotating about its central axis, and looking it up, I find that is 1/2 mr squared. R is the radius of the pulley, and the capital M is the mass of the pulley. Now, because the pulley is rotating, I need to draw a free body diagram on the pulley. So block 1 is trying to make the pulley rotate counterclockwise, and block 2 is trying to make the pulley rotate clockwise. So I can't use sigma F equals ma because this is rotation. I'm going to use the rotational analog, which is a net torque equals I alpha. Now let's calculate the torques. Both forces are applied a radius away from the center of rotation. I'm going to do the clockwise torque minus the counterclockwise torque. And that goes to show you that we can now no longer assume that the tensions are the same. The purple tension, tension number 2, has to be more, otherwise the object wouldn't rotate. I factor out the R. I plug in the inertia. And the R's cancel out on both sides. And I'm going to use a handy-dandy formula that converts from rotation to translational. I plug that in, and the radiuses cancel out. And here's my expression. The difference in tensions equals 1/2 the mass of the pulley times the acceleration. So continuing, I'm solving for A. I multiply 2 on both sides. And now I don't know the tensions, so I have to go back to work that I did previously. So on block 1, we concluded that there is an unbalanced force on the parallel. And on block 2, I'm doing the same consideration. I solved both for the tensional forces, and that way I can substitute the pink tension and the purple tension, getting rid of tension altogether, and now I have one equation with one unknown. I'm solving for A. Okay, so now here's the expression. I'm going to distribute the 2. And I notice I have a double negative 2ma. So that's basically minus 4ma. And I'm solving for the bolded letter A. To solve for that, it has to be on the same side, so I add it to both. And I factor it out. I also factored out mg and 2 on the left side of the equation. I divide by that parentheses, and that's my final answer. Now, I challenge you to plug in 30 degrees for sine, and I challenge you to plug in capital M equals 0, meaning, what if this formula had no mass for the pulley? It should give us the answer we had earlier, and it does. Also, the pulley will slow down the acceleration because the net force not only is moving the blocks, but is rotating the pulley as well. So there will be a decrease in acceleration because of the pulley having mass. All right, guys, that's all I have for today for dynamics review.